One of the ways that we can graphically represent energy is with something called pie charts, or energy pies. And because energy is conserved, the pie represents the total amount of energy. And as the object progresses through its event, the total amount of energy in the system doesn't change, but the energy can get converted from one type to another, or it can be transferred from one object to another in the system. So when we're looking at this particular setup where I have a ball and it's being dropped, by defining my system, I can make sure that my energy is conserved based on what I define. So I'm going to make my system here is the ball, because it has mass and it has a certain position above the ground, on top of which, once I let it go, it's moving. The other thing is, anytime I want to include gravitational potential energy, I have to include the ground as part of my system. The only other thing I could consider would be the air. The ball is, after all, falling through the air. Since in our discussion so far, we've talked about the fact that as objects travel through the air, they do not experience any friction, then I have no energy that's being dissipated because of friction, and so I'm not going to include the air in my system. So the system in this case includes just the ball and the ground. So the ball starts out, it's held some distance above the ground, and it falls straight down. If I look at these dots and arrows, it gives me a sense of how the ball is moving. The dot means the ball is not moving. So at some height above the ground, it's not moving. What kind of energy does the system possess? No movement, so no kinetic energy above the ground, so it must have gravitational potential energy. There's nothing stretching or compressing, so no elastic. And I have no friction, so I have no dissipation. So all of my energy is gravitational potential energy. My ball is starting to move, and I have a short arrow meaning it's moving, but not that fast. The longer arrow means it's moving much more quickly at the bottom. So it's still above the ground, so it still possesses gravitational potential energy. However, because it's moving, now it has kinetic energy. So my pie contains both gravitational potential and kinetic energies. If I look at the diagram, I can see that the ball is above the halfway point. So what that tells me is I have actually more gravitational potential energy in the system than I have kinetic energy. So when I draw my pie, I'm going to show that. The exact proportion isn't critical. You can eyeball it and make your best guess, but it's above half, and it's certainly less than 1/4, 3/4. So somewhere in between is fine. Now if I look at my third position, down here at the bottom, if I look at that diagram, the ball is not quite touching the ground. I see a little bit of white between the bottom of the ball and the ground. So it hasn't stopped moving. The arrow is another indication that it hasn't stopped moving. So I have kinetic energy. And that arrow is big, so that means I have a lot of kinetic energy because it's moving quickly. Now, in terms of being able to measure that height above the ground, effectively that is 0. So I can say that the ball's atoms away from the ground, its height above the ground is effectively 0. It's too small for me to measure it, so that the ball essentially has no gravitational potential energy. All that energy is now kinetic. So if I look at the process of this event, I started out with gravitational potential energy in the beginning, and I end up with kinetic energy at the end. So my total energy is conserved. It's simply been converted from one kind to another. In my second scenario, I have a wind-up bunny rabbit that is walking across a table and eventually stops as the winding goes down. So we can take a simplistic, or we can take a look at this in a more complex manner. Let's start simplistically. So for my system, I definitely want the toy. Now, do I consider the ground? Well, I could, because it's sitting on the ground. But do I have to worry about gravitational potential energy? Well, is it changing height? Not really. It's sitting on the counter or the table. So height isn't changing, so I could completely ignore the ground. But if I look at those arrows, it's slowing down. Why is it slowing down? Well, it's losing speed somehow. Either there's friction or something else is happening. So I do need to include the ground because I have energy that's being dissipated. Again, I'm going to also include the air, and I'll talk in a minute why. So let's start again. Position 1, our bunny is moving, and is moving quickly. Height is 0, so all my energy is kinetic energy. Anytime I am dealing with a system, I never put dissipated energy in the first pie. Why not? Well, when something is starting out, I don't know if the object is going to be moving along and losing energy because of friction, or whether it's going to move along and not lose energy. So I can't determine whether friction is present and therefore energy will be dissipated until my second pi at the earliest. So I never put dissipated energy in my first pi. In my second pi, the bunny is still moving, so I still have kinetic energy, but he's moving more slowly. Nothing's compressing, nothing's stretching, not gaining or losing height, so there's no gravitational, there's no elastic potential energy. But because he's losing speed, I have to put something there, and so what's happening is that energy is dissipating. Now, which is bigger, kinetic energy, dissipated energy? Unclear. Your choice. We're going to say since that arrow is less than half as big as the first arrow, that I have more dissipated energy than kinetic energy, so I'm going to make it like that. But you could make it pretty much any proportions and still be correct. If I look at my third position, there's a dot, no arrow. Well, the dot means the object's not moving, so no kinetic energy, so all my energy now is dissipated. So in this case, what I started with was kinetic energy, and all my kinetic energy in this particular instance was dissipated. How is it dissipated? If you have a mechanical toy walking across a counter, how do you know? Even if your eyes are closed, you tell something is going on because you can hear it. So sound is one way that energy can be dissipated. If I have something that exerts friction because it's sliding along something else, and you figured this out when you rub your hands against each other, you can make them warm. So heat is another form of energy that has been dissipated. If you've got a piece of metal dragging across the concrete, you can hear it. You're warming up both a little bit of the metal and a little bit of the concrete. The other thing you might see are sparks. So light, in fact, can be another form of dissipated energy. In this case, the rabbit's probably not dissipating energy as light, but certainly as heat, very microscopic amounts, and sound, because I can hear that rabbit moving. Okay, let's take a look at something that's a little bit more complicated. We've got 5 different positions for our super ball now. What do you know about super balls? They bounce. So when something bounces, many times we think about it having some sort of elastic properties. And if I look at my diagram, this ball here is nice and round. These balls down here look kind of flat. So they've been compressed. So good bet would be I have some sort of elastic potential energy going on here. If I look at my diagram as well, each time I have the ball in the air, it is lower than the previous time. Well, what's going on? If it's not getting up as high as it did before, then I don't end up with as much gravitational potential energy as I had the previous time. So somewhere along the line, I'm losing energy. Losing energy? That means energy is being dissipated. So let's take a look at what's going on here. If I'm dropping something, we learned previously that my initial velocity is 0. So all I have is gravitational potential energy. So I'll put that in my first pi. Second pi, the ball's on the ground. So it has no gravitational potential energy. The instant it's compressing on the ground, is it moving? Well, hopefully you said no. So I have no gravitational potential energy. I have no kinetic energy. The ball is squished. I bet there's elastic potential energy there. Do I know anything about dissipated energy? Well, not yet, because the ball's gone through the air, and we know air doesn't generate friction, so there's no dissipation from going from the air to the ground. Let's take a look at the next from second to third pies. Second to third pies, I say, it doesn't go up as high. It's in the air, so I've got gravitational potential energy, but it's not as high in the air. Well, that must mean somewhere along the line between when it was being squashed on the ground and going up into the air, it lost energy. So if I lose energy, that means I have some dissipated energy. I don't have very much, so I'm going to put a little bit in. Now the ball falls back down to the ground and gets squashed again. Again, on the ground, not moving, being squashed. So I've got elastic potential energy. Now, once energy is dissipated, that energy quantity can only increase. You can never decrease the amount of dissipated energy in your system. So dissipated energy can only get bigger. It can also stay the same. So going from my third pi to my fourth pi, just like first to second, the ball is falling through the air. Falling through the air means that there's no friction as it falls. So it must mean that dissipated energy is occurring between the ball being squashed and the ball returning to its original shape and position. So that amount of dissipated energy between the third and the fourth pies doesn't change. So that means my fourth pie should have exactly the same amount of dissipated energy as my third pie. Now going to the last pie. I'm back up in the air, means gravitational potential energy. I saw from second to third that energy was dissipated between the ball going from its deformed to its original shape. That means from the fourth to the fifth, the ball is going to dissipate some more energy going from its deformed to its original shape. So I'm going to have dissipated energy. It can't get smaller, it can only get bigger. So I'm going to end up with more dissipated energy. So I'll put it in like that. I'll let you walk through number 4. Pause the video. See if you can come up with energy pies for the first, second, and third positions of the rock. And when you've drawn it on your notes, then you can start the video back up and check to see how you did. In the first position, the rock isn't moving. We're going to make this our ground rather than this line, because then I can say it only has one kind of energy in the first position. It has elastic potential energy. In the third position, I'm going to do the first and the third pies because the ends many times are easier. There's a dot here. That means it's not moving. It's in the air. So I've got gravitational potential energy. No kinetic because it's not moving. Moving through the air means no dissipated energy. So I have gravitational at the end. So now all I have to do is figure out, okay, what's in the middle? I see an arrow for the middle pie, so that means I have kinetic energy. And the rock is halfway between where it started and where it ends, so I have some gravitational potential energy because it's above the ground. And I'm going to say because I made the ground there, it's about half and half. Now, if you made the ground here, then you're going to have more gravitational potential energy. So you'll have some gravitational potential energy here, a little bit. You'll have larger gravitational energy here, and it will still all be gravitational potential energy at the end. Does it matter? No. I think it's easier to set your ground so that if something's sitting lowest down, it starts with no gravitational potential energy. Just makes things a little bit easier. Last one, there's actually 2 different ways you can do this. If I look at those arrows, it tells me all 3 trucks are moving. If I look at the size of the arrows, it tells me all 3 trucks are moving at the same speed. They're not changing height, not slowing down, so no gravitational potential energy, so no dissipated energy, no springs, so no elastic potential energy, so I have kinetic energy. So each truck's moving, the arrow means they're moving the same speed, so I'm going to say that all 3 pies are kinetic energy. And that would be true if my system was just the truck. However, we know that in the real world, when you're driving along, you can maintain the same speed, but eventually your tank runs out of gas. And if you didn't keep your foot on the gas, you'd slow down because of friction between your tires and the ground. So if I change my system and I include the ground, I have to take dissipated energy into account. Great, well, how do I do that? Well, the arrow means the kinetic energy doesn't change. So each of my 3 pies here are going to have the same amount of kinetic energy. But as time goes on, and if I've got the ground and friction involved, that means I'm dissipating energy. So where do I put the dissipated energy? Well, we said a minute ago that as you drive along, your gas tank gets smaller and smaller. So some sort of energy that we're not accounting for right now is feeding into our truck and ground system and supplying energy. So what happens is, as time goes on, the amount of energy in our system, the truck and ground system, gets bigger. So you can feed energy into a system, and that's what we're going to do. So I'm going to make a bigger circle, and I'm going to make dissipated energy the outside portion of the circle. As time goes on, even more energy is going to be dissipated, and so my total circle of energy is going to get bigger. So in this second case, the total system energy increases. In the first case, when the system is just the truck, the total energy stays constant.